Hello and welcome to Chapter 8. We'll be looking at angles, shapes, and their formulas. To begin, we'll start with some angles. There are several different ways to name an angle. For example, I can start by labeling each of these points, A, B, and C. I can then call this angle ABC and write it angle ABC. Or, since this B can only refer to this angle here, I can call it just angle B. Also, I can go backwards, angle CBA. Another way I can refer to this angle is by placing something inside the angle, say for example the number 1. This could then be angle 1. Most of the time you see the name of an angle, it will either use the 3 letters to describe the angle or a number or letter inside the angle to describe which angle it is referring to. To measure angles, we use degrees, and degrees are defined in such a way as that if we go all the way around a circle, we have traveled 360 degrees. So if someone were facing, say, this direction, and they turn themselves all the way around back to facing that same direction, they went 360 degrees. So if I was facing, say, to the right, and then I turned and faced to the left of that, face straight up, I have gone 1/4 of the way around that circle. So I've gone 1/4 of 360 degrees, or I've gone 90 degrees. 90 degrees is always denoted with a little square in the angle to show that it is a 90-degree angle. There are different classifications of angle. If the angle is less than 90 degrees, we call that acute. If it is exactly 90 degrees, we can call that a right angle. And if it is larger than 90 degrees, we can call that an obtuse angle. Then we have our straight angle, which is just a straight line. It represents 180 degrees, halfway around a circle. When I cross two straight lines, I form what are called vertical angles. Vertical angles are angles that are exactly opposite each other, like the 1 and the 3 here, or the 2 and the 4. Vertical angles are always the exact same measurement. So here, the measurement of angle 1 and the measurement of angle 3 are the exact same measurement. So we could say angle 1 is equal to angle 3. Also, angle 2 and angle 4 have the exact same measurement, so we can say angle 2 is equal to angle 4. Another interesting thing here is since we are using straight lines, and straight lines have 180 degrees, we can see here that these two angles, angle 1 and angle 2, add up to that 180 degrees. So here, angle 1 plus angle 2 are equal to 180 degrees. This can be said for any two angles that add up to 180 degrees. This is called supplementary angles. So we have here angle 1 and angle 2 are supplementary. Since angle 1 and 3 are the same, angle 2 plus angle 3 should also be 180 degrees. And we see again here that they form their own 180 degree straight line. So 1 and 2 are supplementary, 2 and 3 are supplementary, also 3 and 4 are supplementary, they add up to 180, and 1 and 4 add up to 180. So these are our supplementary angles, again, adding up to 180 degrees. For something like this here has two parallel lines, and they are being intersected by a transverse line, creating these 8 angles. Again, the same rules as apply as earlier. Here, 1 and 2 are supplementary angles. 1 and 3 are vertical angles. Same goes for 2 and 4. And since these lines here are parallel, what that means is this straight line here is intersecting with the line up top in the same way that it is intersecting with the line down bottom. What that means is angle 1 and angle 5 here have the exact same measurement. We can then draw from that if they have the same measurement, then 2 and 6 are the same, 3 and 7 are the same, and 4 and 8 are the same. So what we can do from that is if we know the measurement of one of these angles, we could then find the measurement of every angle here. Say for example, I know that the measurement of angle 2 is 60 degrees. If 2 is 60 degrees, then 4 must also be 60 degrees, since they are vertical angles. We already know that 4 and 8 then are the same, so 60 degrees for angle 8, and its vertical angle 6 is also 60 degrees. What we can then see here is that angle 4 and angle 6 have the same measurement. These are what are called alternate interior angles. They are inside the parallel lines and they're on opposite sides of the transverse angle. The same goes for 3 and 5. For angles 1 and 7, they're called alternate exterior angles since they are on the outside of the parallel lines and on opposite sides of the transverse. And they also have the same measurement. Now to find 1, 3, 5, and 7, we need to use what we know about supplementary angles. We know 1 and 2 are supplementary, so they have to add up to 180 degrees. So what plus 60 gives us 180? That's 120 degrees, which means 3 is also 120, 5 then is also 120, and 7 is 120. So we really have only two different measurements here, 60 and 120. So if we knew one angle, we could then find the rest based on the symmetry from this. Next, we're going to take a look at polygons. Polygons have all straight lines and they are closed, which means if you start along following the edges of the polygon, you'll always end up back where you started. And the lines do not cross each other, so nothing like that. So these are all examples of polygons. In order to find the perimeter of a polygon, all you need to do is add up the lengths of every side of the polygon. So regardless of shape, if you know the lengths of the sides, say this shape here, we know it has a side of 2, 3, 4, 2, 5, and 4. If we add up all of the lengths of these sides, we find the perimeter of this shape. So 4 plus 2 plus 3 plus 4 plus 2 plus 5. We get the total perimeter as 20, and that will be in whatever units that this is measured in. Say these are all in inches, and this is 20 inches for the perimeter of that shape. We're going to start with our focus on the quadrilaterals. Quadrilaterals are polygons with 4 sides. These are examples of quadrilaterals. We have our square. The square, every side of the square has the exact same measurement. So to find the area of a square, we have area is equal to that side squared. For a rectangle, we have a length and width. A rectangle, all angles are 90 degrees and all sides are parallel. So what we can then conclude from here is that this top length has to be the same as the bottom length, and this also has to be the same as the right width. Our area for a rectangle is area is equal to length times width. This is a parallelogram. The only difference between a parallelogram and a rectangle is the angles are not 90 degrees, but all sides are still parallel. They also, since all sides are parallel, they all do remain the same distance. So if this is length B, then this is also length B. To find the area of a parallelogram, we need to know the height, or the distance between the top and bottom here. We'll call that height, H. The area then of a parallelogram is B times H, or the base times the height. And then this last figure here is a trapezoid, where the top and bottom are parallel and the sides are not parallel. We can call this bottom parallel line here our big base and our top our little base. Then we also need to know the height of this, again the distance from one parallel line to the other. Again, we'll call that H. The area of a trapezoid is area is equal to 1/2 the little base plus the big base multiplied by the height. These are our formulas for our quadrilaterals, the most complicated of which being our trapezoid. So let's go ahead and practice once with the trapezoid formula here. If I know that my little base is 5, say, inches, and my big base is 7 inches, we'll call our height 2 inches. And then to find the area, we just plug in those numbers into this formula. Our area then is 1/2 times the little base of 5 plus the big base of 7, all times 2. 5 plus 7, doing what's inside of our parentheses first, gives us 12. 12 divided by 2 is 6, times 2 gives us back 12. So our area is equal to 12 inches squared. Any unit of area is always going to be squared. It comes from the idea of a square inch, where each side of this square is 1 inch. So this is 1 square inch. Next, we take a look at triangles. We have several different types of triangles. An equilateral triangle is where every side and every angle of that triangle is exactly the same. An isosceles triangle, where two sides have the same length and their opposite angles, so these angles, have the exact same measurement. The scalene triangle then is where no angle is the same and no side has the same length. An acute triangle is where all angles are less than 90 degrees. A right triangle is where one angle is exactly 90 degrees. And an obtuse angle is where one angle is greater than 90 degrees. One interesting thing about all triangles is that if you add up all of their angles, right, the three angles within the triangle, it always adds up to 180 degrees. So if an equilateral triangle has the exact same measurement for each angle and it has to add up to 180, in the equilateral triangle, every angle is always 60 degrees for an equilateral triangle. The most easy triangle to work with is a right triangle. So we're going to take a look at some interesting facts about that. If I label the sides of this right triangle A, B, and C, C here is called the hypotenuse. The hypotenuse is always the side that is opposite the 90-degree angle. And we'll always call that hypotenuse C. One fascinating thing we can do with this then is the Pythagorean theorem, which states that a squared plus b squared is equal to c squared. So if I take the length of A and square it, and add that to the length of B and square it, it will be equal to the length of my hypotenuse squared. This formula is a little more difficult to work with, so we'll take a look at three alternatives. With some rearranging of the formula, we get these three formulas here, each of which solving for a specific side of that triangle. Basically, if I want the hypotenuse, the hypotenuse here is equal to just the square root of a squared plus b squared, which we can easily see here by taking the square root of both sides. A little more rearranging to get either of the legs of this triangle. A here is equal to the square of the hypotenuse minus the square of b, taking the square root of that. And same with b, it's equal to the square root of the hypotenuse squared minus the other leg squared. So if I know that A is equal to 6 inches and B is equal to 8 inches, and I want to find the length of C, I can plug that into this formula here. C is equal to the square root of 6 squared plus 8 squared. 6 squared is 36, so I have the square root of 36 plus 8 squared, which is 64. 36 plus 64 gives me 100, so I have the square root of 100, and the square root of 100 is 10. So C then is equal to 10 inches. And that is how we use the Pythagorean theorem. We can find the area of any triangle using the formula area is equal to 1/2 the base times the height, where the height is the distance from that top point down to its opposite side, and the base is that opposite side. So we have our height and our base. Again, for this triangle, our height would be here, and our base would be this side, B. For a right triangle like this, our height is one of the legs, and our base is the other leg. So, if I have a height of 8 inches and a base of 3 inches, I can find the area of this triangle by plugging it into our formula. So I have 1/2 the base of 3 times my height of 8, and 1/2 times 3 times 8 gives me 12, and then my units are inches squared. So that is the area of a triangle. Isosceles and equilateral triangles have unique formulas for finding the area of those triangles. Of course, if we know the height and the base of the triangle, we can easily solve for the area using our previous formula, a equals 1/2 base times height. However, if we only know the sides of the triangle, we can find them using these formulas. For isosceles, here just plug in the value of b and a, and you will find the area of your isosceles triangle. An equilateral triangle, all sides are the same length, so if you know one side, you can find the area of the equilateral triangle. Just plug it in to this formula here. You can use either a squared times the square root of 3 over 4, or you can use 0.433 times a squared. 0.433 is about the square root of 3 over 4, so it's just rewriting this part, right, with that number there. And that will be a close enough approximation of the area of the equilateral triangle. So let's say we have an equilateral triangle where a is equal to 3 inches. So to solve for the area of the equilateral triangle, we have a equal to 0.433 a squared. We plug in our a squared, so 0.433 times 3 squared. 3 squared is 9 times 0.433. We get 3.897, and our units are inches squared. So that is the area of our equilateral triangle. This here is a hexagon. A hexagon has 6 sides. Each side has the same length, a, and each angle has the exact same measurement. For a hexagon, every angle is 120 degrees. The formula for the area of a hexagon is found here, and you can either use this formula here, which is the exact formula, or its approximation, just finding 3 times the square root of 3 divided by 2, which gives us 2.598, times that a squared, where a again is the side, one of the sides of the hexagon. Some more measurements of the hexagon. The distance from one point to the opposite point, we'll call that d. D is always twice the length of a, so d is equal to 2a. However, the distance from one side to the other, we can call this f. F is about 1.732 times a, so not quite twice a, or a is equal to 0.577 f. So let's say I know the distance from one point to another. I know d is equal to 6 inches. If I want to find the area of this hexagon, then I can plug it in here, but first I need to find a. If d is 6 inches, then a is half of that, it's 3 inches. So we can plug that in here. So we have 2.598 times 3 squared. 3 squared is 9 times our 2.598 gives us 23.382, and our units are still inches squared. So this then is the area of our hexagon. Sometimes we have irregular shapes that we want to find the area of. So what we can do with something like this is break it into pieces that we do know how to find the area of and work with that. So for example, this piece, if I cut it here, I can see that I have a triangle and a rectangle. The rectangle then has a width of 16 inches and a length of 32 inches. Formula for area of a rectangle was length times width. So the area of that piece is 16 times 32. The triangle we see has a height here of 20 inches, and the base then is this side here. Well, we don't have the exact measurement of that, but we can figure it out because this side here, and this is the opposite side of that rectangle, and rectangles, their opposite sides are the same length, so this must also be 16 inches. So we have now our triangle with a height of 20 and a base of 16. So the area of that triangle is 1/2 the base of 16 times our height of 20. So the area of the rectangular part is 512 inches squared. The area of our triangle then is 1/2 times 16 times 20, or 160 inches squared. To find our total area, we add those together. We have our 512 plus 160. So we get our total area of 672 inches squared. This is our general tactic for any irregular shape. Just cut it into pieces that we do know how to solve and work with those pieces. Add up their areas to find the area of that shape. The last section we will cover is on circles. The circle here has a center. From the center of the circle, every point along the circle is the exact same distance from the center. That distance is called the radius. The radius is that distance from the center to the edge. The diameter then, d, is the distance from one side to the other of the circle going through the center. So that means our diameter is 2 times the radius. Our circumference then, right, rather than calling it a perimeter, the circumference of a circle is the distance around the circle. The circumference is 2 times pi times the radius, where pi is about 3.14. Of course, pi is an irrational number, which means it goes on forever and never repeats. We just approximate it to be about 3.14 for our calculations. So 2 times pi times the radius will give us the distance around the circle, and the area of the circle is pi times the radius squared. Those are our formulas for a circle. So if I know that my diameter is equal to 8 inches, and I want to find the circumference and area of that circle, I first need to find the radius. The radius is always half of the diameter, so my radius is 4 inches. My circumference then is 2 times 3.14 times 4. So 2 times pi times 4 gives me 25.12, and my units are still inches squared. For my area, I have 3.14 times 4 squared. 4 squared is 16 times the 3.14 gives me 50.24, and my units are still inches squared. So that is the circumference and area of a circle. So let's say I wanted to find the area of this washer here. I know the distance from the center to the inside edge is 3 inches, and the radius from the center to the outside edge is 9 inches. In order to find the area of this, I could find the area of the larger circle here, and then subtract from it the area of this opening. So the area of the larger circle is pi times the radius squared. That radius is 9, so 9 squared, and the area of the inside circle is pi times 3 squared. We have area here. 9 squared is 81 times pi, again assuming pi to be 3.14. We get area as 254.34, and our units are inches squared. The area of the inside part, we have again 3.14 times 9, so we have 28.26 inches squared. So in order to find the area of our shaded region, we take our 254.34 and subtract from it our 28.26. This gives us the total area of 226.08 inches squared. So that is the area of this yellow washer. That will do it for Chapter 8. Don't forget to take notes on this and bring your homework and questions to class next week. I will see you then.